All right, this code is going to implement the bisection method, and we're going to look for a root of the function cosine. Of course, that function can be changed, but let's go ahead and do it. I assume you're familiar with the theory of bisection method. Basically, you're dividing an interval in half each time and finding out if the root is to the left or to the right. So let's go and we'll follow these commands here, see if we can do this. So first of all, we know that we're going to use NumPy and we're going to be plotting. So we want to import NumPy, from NumPy, import star, and then pyplot, and then say from matplotlib.pyplot, import star, and then we want to display inline, so matplotlib inline. Okay, good. All right, so that's going to get us set up. Now, first we want to initialize. So I want to define a function where I can change the function that I'm finding the root of very easily. So to define a function, I'll put def. Let me just call it fn. Fn has one argument, so I'll say fn of x. X is a good variable to be unknown, so put the colon here for def, and the value of this function will be, in this case we want cosine of x, so I'm going to return cosine of x. Okay. So let's set the desired error tolerance, and in this case I want the tolerance to be 0.0001, so that's 1 over 10,000, so I'll just call tolerance equals 0.0001. Now, the number of iterations, I could use a formula to calculate the number of iterations necessary, but I'm going to be lazy and just specify enough iterations so that the tolerance will definitely be met. And I'm going to call that number of iterations max it. So max it equals 100. So 2 to the 100 is a pretty, or 2 to the minus 100 is a pretty small number. So I can be pretty sure that the tolerance is going to be met before it does 100 intervals. You know that the accuracy increases by, the error is divided by 2 each time. The maximum error is divided by 2 each time. So let's guess for the lower and upper limit. Now we're finding the root of cosine. And we actually know that cosine has a root at pi over 2. So I'll say my lower and upper will be 1 and 2. And the upper equals 2. Okay. And then I want to create an array for the error results because I'm going to want to keep track of the actual error. In this case, I want to plot the errors as we go. Now, in practice, you wouldn't need the errors as you go, and of course, you wouldn't know the actual error, but this is just to show how good the algorithm is doing, so you can understand pretty much what's going on with the algorithm. All right, so for the first array, I'm going to call this max error, so I'll call it max error. And I'm actually going to get an value of error for each iteration plus the initial value of error. Okay, so it's because there's a theoretical error at the beginning, so I have zeros. So that means that I'm actually going to need in order to make sure that I have enough space, I'm going to need max it plus 1 places in this array. So I'm going to put max it plus 1 because like I said, if it's conceivable, I could do 100 arrays, which would give me 100 different errors, plus the initial error, so that would be 101 errors. Right? So I also want to do something, the actual error that is, so let me call this actual error. Also max it plus 1. Okay. And then we actually know, what the actual root is. This is for theoretical purposes. Of course, you wouldn't know this in general, but just to compare, in this case, theory with practice. So actual is going to be equal to pi over 2. Now, you know NumPy has a pi, so NumPy will understand what pi is. And then let's start the algorithm off. Now, the algorithm uses successive averages. So you know this is the midpoint, so I'll call it AVG. I could have called it midpoint or something like that, but AVG is lower plus upper over 2. All right. So now I'm ready to continue, and what I'm going to do is going to evaluate the function at the average, see if it changes sign in the left half or in the right half, and decide where to look in the next interval according to the result. Okay, so let's do the calculation. All right, I know I'm going to need a loop, and in fact this case I'm going to use a for loop because I know that I want to go 100 times. Well, of course I won't go the whole 100 times, but I want to allow for going 100 times. So I'll do say for I in range of maxit. I'm going to need my colon. Now let's go ahead and calculate my max error and actual error, because I do have I do have a max error and an actual error even at the very beginning. So I'm going to calculate that at each iteration. All right, so first I want to start out with a max error, and this is max error of I. And what's the max error going to be? Well, it's actually going to be, you could do upper minus average, or you could do average minus lower. I'll just do upper minus average. It doesn't really matter. Okay, and then for the actual error, I'm going to take my estimate at this point is average, so the actual error is going to be equal to the absolute value, because I'm just looking at absolute error. It's absolute value of AVG minus actual. All right, so that's my actual error. All right. Now, at this point, it's possible that I've already met tolerance. So I need to check that and see if the max error is less than the tolerance. So I'm going, whoops, sorry, I did MATLAB style. These are square brackets. Would have caught it in debugging, but that's okay. You always make mistakes and have to go back. All right, so let's see. So I'm going to say if, now the max error is max error of I. Now I'm not going to use actual error because in practice I wouldn't know the actual error, but I would know the max error. So if max error is less than or equal to tolerance, and then I'm just going to get out of the loop. The way to get out of the loop is just break. Okay, so that will get me out of the loop, and eventually that's going to happen because the max error is going to divide by 2 each time. Okay. All right, so now let's narrow down the location of a root depending on the signs. So the first option is if average is a root, then I need to exit the loop. Okay, that's going to be an if statement, so I'm going to say if. Now average is a root, that means that fn of average, fn is the name of my function. Remember, I define that up here. So Python understands that fn is cosine in this case. So if fn of average is equal to actual, in this case I'm going to exit the loop, so I'll just say break. All right, now on the other hand, if fn changes sign on the left, then I'm going to move to the left interval. So that's elif. So the change sign means that if I take the function at average times the function at lower, then the sign is changing. So elif fn of lower times fn of average is less than 0. Now in this case, what am I going to do? I'm going to set the upper as the average. The lower limit stays the same, but the upper limit becomes the average. If you don't understand that, go back to the theory and you'll see that. All right. So the last resort is else, and in this case, we're just going to take the lower limit as the average. Okay. And that's all I have to do. That's all the iteration I'm going to do. It'll automatically keep going until I either get exactly the root or I get to tolerance. Now I would like to point out that there's a little bit of a, I can say, inefficiency in this code, because you actually evaluate fn of AVG twice, which is not really necessary. You could have set fn of AVG as equal to a variable and called that variable. So save a little bit of calculation. Not too big a deal, but if you had a function that was hard to evaluate, you wouldn't want to do fn of average AVG here and fn of AVG here. Sometimes that's a consideration. All right, but we're done. So let's go ahead and print the results. I'll print. You can say estimated root is, and then put here, and then it's AVG, and then this is with tolerance, and then this would be tolerance. Okay. Well, words are pretty dry and lifeless, so let's go ahead and present the results in a figure. So we'll have figure 1, okay, and we want to plot the maximum and actual errors versus iteration number. Now, where are the max and actual errors? Well, they're in these arrays max error and actual error. Unfortunately, there's a problem because these errors are large. In fact, in my current case, because maxit is 100, they're going to have 101 entries. Lots of them are going to be zeros because I'm not going to use them. So I only want to plot up to the points that have been calculated. So how do I figure out how many points have already been calculated? Well, after you're done with a loop, I will take on the last value that it attained. So in fact, as I goes from 0, 1, 2, 3, and so on, the non-zero values of max error and actual error will also be put in. So the last value of I is actually the index of the last non-zero values of these two. I do find a small issue here. Before I said I want to have max it iterations. So if I wanted to include max it, I would have to put a +1 here. Very small issue. It's very unlikely you get that far anyway. All right. So so what we want to do now is in the plot, we only want to plot from index 0 up to, and it would be actually including or not including index I. All right, so I've confused myself a little bit. I need to figure out, does it include the last index I or it doesn't? And in fact, it will, because the value of I when you leave this loop is the last value it's written to. So I want to get the iterations from 0 up to I. So when I do the plot, that's actually going to be I plus 1 values. Okay, so I'm going to plot first, and the first thing I'm going to plot is the iterations. So the iterations go from 0, as I said, 0 to I, so that's going to be a range of I plus 1. And then along with that, I need the values. So first I'm going to do max error, and I want to start with 0, so I can just put a colon there, and I go again to I plus 1. Okay, and then let me put a label on it. Okay, so that should be my first plot. My second plot is going to be similar, so I'm just going to copy this and modify. Same range, instead of max error, I want actual error. Might as well and just put this as actual error. Okay, whoops, actual error. Okay. And let's do scales. I want y as a logarithmic scale because when you're dividing by 2, that means that you're basically doing a multiplicative error. And you want to turn multiplicative into something additive that looks like a straight line. You always want to use a logarithmic scale. You'll find that logarithmic scales are very common in numerical analysis because many errors are logarithmic. So let's say this is going to be y scale equals log. Okay. All right, and then add labels to axes. So we'll do that. X label, and this is iteration number. And then Y label is going to be errors. And I guess absolute errors. Okay. And then I want to add a legend and a title. Now if I just say legend, it will try to print it, put the legend somewhere, but I'm going to put legend lock equals 3, and we'll see where that puts it. And then I want to put the title, and we'll say title, and then this is errors. Let's see, we can say, so I can say or max and actual errors for bisection method. And then we do show. And the proof of the pudding is, does this work? So let's go ahead and execute. I've already loaded Python, so this should go pretty quickly. All right, now here I have some invalid syntax. What did I do? Well, I'm still thinking MATLAB here. I put parentheses instead of square brackets, so that's easy fix. It's fortunate that I've gone this far down in the code without any error. Now let's see if there's any other square brackets I've missed. Let's just scan through. Here's another one. And I think I don't see any others. That looks good. Okay, so let's save that and go again. And here it says, oh, whoops, I missed something here. I missed the square bracket. How did I miss that? Okay, let's try again. All right, so here we have this. And wow, something is screwy there. Let's try to figure out what's going on. All right, let's look at my graph and see. All right, let's look at my graph and see. Well, one thing I see here is that this is not a log scale. So there's something wrong here. And in the meantime, I looked up the syntax here, and this is incorrect. That scale should be log here. That should be like that. So that's not a log scale. So we'll fix that. But that's not the only problem. It went out to 100 iterations, and the maximum error didn't change. The actual error was kind of small because, in fact, 1.5 is close to the actual value, but something didn't change. So something's not getting updated. Now let's look at my loop again and see what's going on here. Well, what did I do? Well, I certainly, when I went through here, I updated upper and lower, but if you look in the code, I never updated average. I never changed the value of average. So average always stayed the same thing, even if upper and lower changed. Right? So I need to, after this, I need to say AVG equals, let's see, it's going to be upper plus lower, or lower plus upper, over 2. Now I could have avoided this by putting this one inside the loop, but this is okay. It's just it's not a big deal. So we'll just go with the flow and see if it works now. All right, let's see if we got something more. Okay, so we have here. Y-scale log is not correct. Let's see if I can figure out what's going on here. I think maybe it's a word, so let's put a parentheses there, like that. Let's see if that's any better. And we'll see, oh, that looks nice. Okay, very pretty with the estimated root. And here's your cookbook method for bisection error.